can share this presentation. All right, so thank you for that introduction, Win, and I'll just see if I can mute that. Okay. Now, we've had most of the presentation. Thank you. I will mention a little bit more, therefore, on what motivated me to get involved with nuclear energy. Up here in the Southern Highlands, about 15, 16 years ago, I started a climate change group. And initially, I was very interested in the potential for renewables, that's primarily wind and solar, to address emissions reductions. The engineer in me clicked into gear, and I was concerned not only about the variability, but the stochastic variability. In other words, you could have variability like we have with solar, but in respect of wind, it can be very highly variable and unreliably variable. I got in touch with Dr. James Hansen in the United States, who's sometimes known as the grandfather of climate change science. And together with the St. James Ethics Centre in Sydney, we brought him to Australia. And after a lot of discussions with James, I became aware that nuclear energy was the likely way to address emissions reductions. Now that folded then into why I undertook the Masters at ANU in nuclear science. If I was going to promote this technology, I needed to learn a lot more about it. So today's talk is Nuclear Power, Australia's source of clean energy and climate solutions for a century. You'll notice on the side of the screen, apart from myself, is Dr. Robert Barr, who's a colleague of mine, a very valued colleague, and he lives in our area. He's down in Kiama. Some of you may know Robert, and he's designed an excellent model, which we'll talk about later in this talk. So this discussion today will go into 4 specific areas. Who wants low cost, low carbon nuclear energy? 2, why build nuclear energy, its cost and reliability compared to other low carbon options. That's where Robert's input is valuable. Then we'll go into what could we build, and finally, where would we build them and how long would it take? So who wants it? Well, we're seeing anecdotally a tremendous move, I believe, in our communities. Your group is one example, but I'm booked up now through till June with community groups who are interested in talking about nuclear energy in Australia. This is a poll that was done by Compass Polling in about October. There were a number of them done towards the end of last year. It's a somewhat loaded question. And what was put to the people polled was that nuclear technology is used to generate much electricity in advanced economies like France, USA, China, Sweden, UK, and Canada. Its safety and reliability have improved considerably in the last 20 years. Do you think Australia should reconsider nuclear in our plan for cleaner energy and meeting our Paris Agreement targets? Now, given that's a slightly loaded question, roughly two-thirds, or 63% of the respondents said it should, 37% disagreed. A more balanced question was put by Essential Polling on the 28th of October to about 1,500 people, that's right. To what extent do you support or oppose Australia developing nuclear power plants for the generation of electricity? 50% supported, 32% opposed, and with 18% unsure, I'd suggest that that probably gets nuclear just over the line. And finally, this poll came from Newspoll, again done in September, October of last year. And the question there was, the US or UK will supply nuclear propulsion to the submarines, and Australia hasn't committed to developing a homegrown nuclear industry. In the future, do you think Australia should develop its own domestic civil nuclear industry, including new nuclear power stations in Australia to generate electricity? 61% were in favour, 27% against, 12% didn't know. And even amongst the Greens, it was about 47% thought it should actually be considered or definitely agreed with it. So I think what we're seeing in the Australian body politic is that Australians really want this issue considered. We have laws against it, and we have governments procrastinating, and some of our parties are not moving ahead with it. But I think the Australian people want to see movement on this. So why build nuclear energy? Well, for a dry climate, nuclear fission is the only proven means of achieving economical ultra-low carbon energy. And I say that in a dry climate because hydro can do the work in some nations. We see people in Southeast Asia trying to do it. We see some in parts of South America and some in the Nordic countries. But in general, fission looks to be the only way that a country like Australia could achieve economic low carbon energy. Nuclear is reliable. It's established that now for a great many years, particularly the light water reactors. It's low cost. For example, in the Nordic countries at present, they're generating at about $20 per megawatt hour. You're seeing similar numbers in Texas, for example, with their nuclear power plants. In Korea, they're generating at about $30. So it is a low cost source of electricity. It's low carbon. Again, the Nordic countries calculate they're running on about 6 grams of carbon per kilowatt hour. The French are at about 12. And in the northern latitudes, we're seeing solar at about 85. In our backyard, it's probably down around 50. So it's definitely got the wood in terms of being low carbon. Importantly, for communities, we see that because the plants will run for 60 years minimum and probably 80 with license renewals, it's tremendous for regional renewal education and wealth generation because it can certainly stabilise communities around strong industrial growth. It pays very well. It's a very clean industry, and the workers, predominantly the tradespeople who are educated up in it, are well educated and are very well remunerated. And finally, it's the most sustainable in terms of the use of non-renewable materials. The system based on nuclear is operating about 5 or 10% of the non-renewable materials of wind or solar. I'll come now to the underpinning of the case for nuclear in terms of its emissions and economics. And this quite complex looking image is going to take some time to explain. What we have going up the vertical column, that is the amount of power being generated or consumed in terms of megawatts. Along the base here, this is for a month of June. The dark black line that we're seeing here that I'm wandering around, that's our energy demand that is actually met. Now, I'll explain the colours in a minute. What Robert Barr did was he took the energy demand in Australia over a 3-year period, that at half-hourly intervals. That was 52,560 data points. Then he was able to take that generation, that energy generated, and dissect that into wind, solar, open cycle or combined cycle gas, and different forms of coal, for example, black coal or brown coal. By being able to dissect that into wind and solar, you effectively get a sampling over a 3-year period, which is affected by the weather or the time of year. So your sampling enables you to say, okay, in a 3-year period, we have a known amount of solar capacity, and this is the type of trace that we would get if we tried to use solar. Likewise, we can do it for wind. And we know, for example, that wind is randomly variable. And what we find with wind, for example, is that in June 2017, wind put out about half the energy of June 2016, 1 year before, despite having more wind capacity. So what we see with the problem with renewables is this random variability. We can track that in this model. Now, in the model output we see here, this is for AEMO's Integrated System Plan, fast scenario in 2042. So this is what AEMO are telling us our power system is going to look like in 2042. We'll have some brown coal, some black coal, the salmon color, that's combined cycle gas turbines. The blue is hydro, the gray is open cycle gas turbines. The green we have here is wind. This pink color, that's storage. And then the darker yellow here is utility solar, and the lighter yellow is rooftop solar. And the orange here is what we call spilled energy. And so we see a considerable variability. Some days we have almost no spilled energy. For example, these two, other days we have a lot. And so this is a very complex system because we've got to try to manage these base load power plants while solar goes right through them. It prevents them just providing energy to the grid. And so they either ramp up and down or they have to steam off and waste the energy they're generating. We go into the next graph or image, and this is an integrated system plan going along AEMO's forecast of what we would get with 100% renewables. And in this case, we need to ramp up the amount of storage dramatically to 21 gigawatts of pumped storage. That's all of this pink stuff in here. Now, to put that in perspective for you, Snowy Hydro 2 is 2 gigawatts of pumped storage. We've already got in the system about 700 or 800 gigawatts. So we're talking about a massive acceleration of the pumped storage that hasn't even yet been completed in Australia, about 2,700 megawatts. I doubt whether that is actually feasible in a dry climate such as Australia. If you go through 2 years of drought in the Great Divide, I'm not quite sure how that could ever be achieved, but proponents consider it can be. What we see under that situation is the spillage is going up. Why is spillage going up? It's going up because of the amount of overbuild you've had to put into the system to cope with a day like this one, when you're only just meeting demand. And so we have here massive amounts of spillage, but on this day, for example, there's almost no wind preceding it. Down here in the green, very little wind, and it's probably cloudy as well. So the renewables are basically gone out to the woodshed for a while, and they're not doing the job. So this becomes a very expensive and difficult system to manage, particularly with that spillage. Now, some proponents are suggesting the surplus energy can be used to manufacture hydrogen, for example. But I don't think they're really looking at a graph like this, because there's probably many of the people in this audience today are engineers from industry. I know that almost all industrial processes like to work at about 90% capacity. Here, we've got such variable amounts. Sometimes you've only got about 2 hours of spillage. Sometimes you've got maybe 6, and sometimes you've got almost none. And the thought of putting that surplus into storage to give you a uniformity of delivery of energy into electrolyzers is a bit fanciful. The other problem we have with this system is a huge increase in the amount of transmission that's going to be required to enable it to ever occur. And we're going to discuss that right now. What our model has found is that when you go to large amounts of renewable energy, you have to go to more than twice the existing transmission levels that we currently have. That's because of the significant overbuild and the low capacity factors that we have with wind and solar. Now, this is a simplified conceptual diagram of our current system. What we have here is Sydney is the main load. It receives its energy in this stylized diagram from the Hunter Valley. Of course, there are other locations. You've got the mid-north coast, but it's a stylized idea. So we're getting a lot of energy coming in from these large power plants over fairly short distances, about 100 kilometres or so as the crow flies. That energy then goes out to regional centres such as Dubbo, or larger centres such as Canberra, or even down to Wollongong, for example. And then at times it's backed up by energy coming back from the Snowy. And so that flows back this way. And that's roughly the architecture of our existing system with no renewable energy zones. When we go to these 100% renewables with remote renewable energy zones plus added pump storage, we see a radical change going on to the grid. The existing transmission, much of it becomes redundant. Some of it will still be linked, for example, to renewable energy zones in the north of the state, but the vast majority of it becomes redundant in this region. Instead, we're now building the same sorts of capacity out to each renewable energy zone over 2 or 3 times the distance that it currently does. In addition to that, when we have excess to demand, that surplus goes down to pump storage, in this case to Snowy 2.0, but it could be going to other pump storages. That power then has to come back from the Snowy through the Canberra load through to Sydney, or via switchyards here. So we're building additional transmission capacity all through the state to manage these renewable energy zones. We're doing it over longer distances with much greater redundancy because we know that these renewable energy zones are operating at capacity factors down around 25 to 30% compared to coal plants, which can get up around 60 and 70%. So that's reflected in the overbuild of the transmission grid. So this is going to see a doubling or tripling of the amount of cost going into transmission. Now we know that AEMO have already said that they're going to need at least 10,000 kilometres of new transmission to unlock these renewable energy zones. That's a massive amount. And that's what's going to underpin this increase in cost. We saw a recent issue with Transgrid's projection to build a new link down to Snowy Hydro 2. It was to go, or it will go, from Bannaby, which is just out the back of where I live in the southern Tablelands, down to Wagga and then off down to Snowy 2.0. The original estimated cost was 1.3 billion. It's now looking at $3.4 billion to build that link. I don't think government and people promoting these renewable energy zones have really got their handle on the sort of estimates that we're talking about for this transmission. And so there is a tremendous amount of risk here. 45% in New South Wales of our bill, retail electricity bill, is transmission and distribution. Down in South Australia, it's up around 65%. So we're talking about multiplying the dearest part of our bill by 2 to 3-fold. And that's going to have a profound effect on our electricity costs.
Not to mention all the losses.
Correct, not to mention all the losses. So what are the options? Well, clearly, if we're going to be hitting the highest part of our bill with a 2 or 3-fold amplification, why not try to use the grid as is without any amplification? And that's where the nuclear issue comes in. Now, some people suggest, oh, well, we could have nuclear to back up renewables if it doesn't work, which is an appeasement concept of the first order. And a little bit of thought around why that's not a really good idea is shown in this particular image. This here in light blue shows 50% of the nuclear energy on the NEM coming in. The blue again is hydro. Here we've got solar and we've got wind. If you put nuclear into a system where solar gets priority access, you're going to drive the capacity factors of your nuclear plants down exactly the way is happening currently with coal. But you've paid handsomely for your nuclear plants, and that's not really a very sound economic argument. So you either drive, if you allow wind and solar to have priority access, then you'll drive up your costs of nuclear. Your other option is to have a firmed up power purchase agreement for your nuclear and try and turn your wind and solar into truly dispatchable energy sources. To achieve that requires massive amounts of storage, which will drive up the costs of wind and solar. So there are compromises on each side of that equation if you're to try to do this. I'll pass through that, but this image just shows the increase in the cost of nuclear with a reduction in capacity factor. I'd suggest to this audience it's abundantly self-evident, that sort of thing. In our modelling, the most effective, lowest cost emission scenario and most economic output was this one. This is a mix whereby nuclear effectively comes up to the evening base load, much as coal did in the past. And for the diurnal range, night to day, we have solar operating with limited amounts of storage and with our existing hydro. The amount of storage we've got here is of the order of 4 gigawatts. Now, I've said before that Snowy Hydro 2 is running in at about 2. We've got about 700 or 800 at present. So at about 4 gigawatts of total storage, that's a conceivably sensible or manageable amount. So under this energy mix, we would see solar utility in there at 11%, rooftop solar at 6%, existing hydro at 7%, and nuclear at 76%. And that would give grid emissions of 22 grams of carbon dioxide per kilowatt hour. But importantly, because we're talking about 300 megawatt nuclear plants in this scenario, there would be almost no grid amplification required to handle this situation. You would build those nuclear plants at the nodal points of the existing grid, for example, where we have our existing large power plants. Here's a 3-day plot of the mechanism that we're talking about. The dark black line is your demand, morning through to evening. Through the day, the solar comes in, but you don't put more solar into the system than can be addressed readily by the nuclear power plants wrapping up and down modestly. The surplus generation here is going into storage. The sun goes down, it comes out of batteries or it comes out of pumped storage, and you have the hydro backup. And so you get a very manageable system. Wind, you'll notice, is not used in this system. The random variability of wind means that you end up having to put a lot of redundancy into your system to handle that randomness. You'll probably never get off building gas turbines if you're to try to put wind in there. So that's been left out quite deliberately. In this image, we see the results of 6 scenarios that have come out of the model. And I'll explain them now. Up the left-hand side, we have the cents per kilowatt hour for energy that's being provided by these scenarios. The blue represents the generation cost. That, if you like, is the current market cost of wholesale energy. The grey increment, that's the differential cost to high voltage customers. For example, BlueScope or Blue Circle Cement near where I live, or Sydney Trains, for example. And this amber colour, that's the differential to low voltage customers. For example, normal commerce or retail customers such as ourselves. The first of these mixes is the existing generation mix. That's generating at about 700 grams of carbon dioxide per kilowatt hour, and we're at about 25.5 cents per kilowatt. And that's about the retail level that we're currently seeing. So our model is working, keeping in mind we're putting in actual costs of plant. If we go here to 100% renewable energy and pump storage, we see we're jumping up to about 42 cents and we've got 24 grams of carbon. We're jumping up here because of the redundancy that's going into the system. Then we've got this impact of transmission and distribution. If we go to AEMO's step change, this is their favoured program out to 2042. We've got us still jumping up above 38 cents and about 100 grams of carbon. Or we go to a more conservative change that AEMO are pushing, which is their central scenario, which has got an unacceptably high level of emissions at 348 and is still more expensive than the current situation of about 29. The compromise between trying to mix 50% nuclear with renewables, and there is also a bit of gas in there to address the existing wind. That is a bit of a problem. We've got 44 grams. It's a compromise solution. The best solution we came up with is this 76% nuclear. It's actually slightly lower than what we're currently paying. It's down around just under 24 cents for retail, generating at around about $82. And we've got 22 grams of carbon per kilowatt hour, which is a highly desirable level to get to. Now, I'll just leave it there briefly. As I said, I'll take questions because the next thing we're going to go to is what we would build and why. So have we got any questions along the line yet, please?
Roger, you might just check the screens and see if there is one. Could I just ask the first question?
Yes, Win.
And I noticed there's not much mention of battery storage at all in any of the calculations. There's a little bit, I think, on one of the last screens. Is battery storage not going to come on stream to be able to provide some of that that redundancy that we're looking for?
At present, most of the durations and the amounts of energy we were looking at run, we need to have storage in place that can run for probably 12 hours or more in the model. And at present, while we put battery storage in there and we ran a number of models, we used, for everything except nuclear, we used the costs coming out of CSIRO's Gen Cost report. And what we found when we put those in and we tried to ramp up the battery storage, they were more expensive than using pump storage. Now, we hear a lot of hope that battery storage will come down. But on the current costs that we got from CSIRO's report, which is what we used in the model, battery storage was more expensive than pump storage. That's the reason why. It does figure, but only over the short term. If you remember going back to the 3-day one,
yep,
we had battery storage in there for the first couple of hours, and that was running in parallel with pump storage for longer durations.
yep. Okay, thank you.
Graham Solomon has a question.
Well, I was interested in that last graph you showed us.
Yes.
A lot of the models not only show, a lot of the situations not only show the increase in total cost, but say the 100% renewable plus pump storage. The top of that light coloured bar is just that would be the cost to like heavy industry, wouldn't it? Which is
No, the cost to heavy industry would be 26 cents.
yeah, which is a long way up on the existing system.
Correct. That's right. The existing system down here is at about 15.5 on a cost basis. So you're getting nearly a doubling to industry. Yes.
So I'm just checking here, what I can sort of see there is not only you're paying almost twice as much for your electricity, you're paying almost twice as much for everything else. Because
Correct.
all the manufactured goods are going to have to go up. Steel and things will go up in price their way.
That's quite correct. And I'm hoping today in this presentation, as I get into where we're going to cite these, one of the reasons is quite sad that we can't do this face to face, because I really need out of your group commentary on the applicability of these in the Illawarra region. I hope if we don't cover it all today, I hope this can be an ongoing dialogue to build out these concepts for the Illawarra. So we'll come to that further in the discussion.
Thank you.
Roger.
Robert, do your costs also take into account the additional costs associated with frequency and voltage stability? You know, there's nothing like big rotating machines to keep things nice and stable, which you would get from a nuclear system, but you know, they're putting in synchronous condensers and so on at the moment to do it.
Yes, what we did within the transmission and distribution portion of the model, there's currently under our bills in New South Wales, for example, we're paying about $1.50 or so a megawatt hour for that sort of facility, and that's rolled up in the transmission and distribution component. It's not identified discretely, but when one goes to the makeup of a bill, it's rolled up in our transmission and distribution, and I'll summate that later. But that will increase. I mean, you go over to a place like Western Australia, where they're paying the best part of $5 and $6 for that ancillary service. Currently in New South Wales, we're not at that level yet, but we could get there.
Thanks.
All right, if there's no further questions, back to you, Robert.
Very good. Thank you for those.
I have one.
Yes, I've just got a question,
Yes,
Gwen, if that's all right. Yeah, Robert, the analysis you've just presented to me is you know, really based on common sense and sound information, and I've been puzzled for some time by why this kind of argument fails to convince people who seem to have set views, for example, from the Green movement, who just don't seem to want to get it. I know it's maybe a little bit provocative, but do you have a view on that?
Yeah, I deliberately get involved with those groups to try to understand. Look, at the larger level, one only needs to go to Germany, all right? And we've seen in the last month, Germany turn off 3 nuclear power plants because they've got a national phobia about nuclear. that phobia is fed through into a lot of the narrative that we see in countries like Australia around the Greens Party. I see the same dialogue. It's an international trade in narrative. I don't fully understand this existential fear of it, but when we looked at that news poll result, we saw that there is a turnaround in some of the green movements. We know, for example, in Finland, the Green Party there endorses nuclear. So I think at the margin, we will see some change, but there is something going on in Germany. How on earth they could turn off nuclear power plants, some of the best in the world, and now they're buying more gas and coal, and the power prices in Europe right now are crazy. So it is inexplicable, but I hope at the margins we're starting to see a change. I don't have a great, I'm sorry, I'm flubbing your question really, because you're asking me almost a psychological question of why is this existential fear of nuclear? I don't really get it. I'll tell you, I went to Fukushima and I took my Geiger counter around Fukushima province. And I tried to find high levels of radiation in Fukushima, okay?
Yeah.
And I've got to admit that I'm walking around and I'm a baby boomer who grew up in fear of the bomb, and I'm sitting there measuring this stuff and I'm saying, gee, I'd find a few warm spots, you might say. Nothing of any lethality, of course. And I must admit there's a level of anxiety even kicks into me. But I had to say, hang on, Rob, this is science. So I think in all of us, there is a little bit of this anxiety with it. And you just have to be disciplined about it and say, no, what is the science? What are the measurements? You know, get to grips.
Yeah, thank you. Yeah, and interestingly, I recall seeing data from, it's probably a decade ago or so now, that the operating efficiency of Germany's wind turbines was 4%.
Well, I mean, their solar's down around 8 and 9 at present, capacity factor. I mean, it's just ridiculous.
Yeah.
Okay. I'll just move now to our next part of our presentation. So what would we build and why? Well, the first thing I'd like to address is the passivity we seem to suffer in Australia over waiting for things to be developed offshore. And I want to be quite firm about this. From everything I'm learning, the future of nuclear is in our hands. We can drive decisions made by vendors. The technologies are out there. If we're not taking them up, it's not because the vendors can't provide them, it's because we're not providing the right signals of wanting them. Now, we're seeing some extremely exciting things coming out of Canada right now. Our Commonwealth cousins there in Ontario Power Generation have just done a deal with General Electric to build a 300 megawatt plant at their Darlington site, and that's going to happen. And we should be combining with the Canadians on this. So the lowest cost option that I outlined earlier requires 24 gigawatts of installed nuclear power capacity, which is the equivalent of 80 number 300 megawatt small nuclear units. These are expected after 2028. But that doesn't mean that, one, we can't get rid of our legislation preventing them, and also start the planning and options evaluations now. That could be happening right now. There is no reason to wait for doing that sort of work. The options could include large nuclear power plants in places like the Latrobe or the Upper Hunter or the Mid-North Coast or Gladstone. And so the options could include 10 large nuclear plants and some small ones. So you could have a hybrid system. As engineers, we always know, you know, it's a matter of degree. It's never in absolutes. And we could be looking at both, but we need to be getting on with it. What we are looking at in the evaluation at present is this plant. This is BWX 300. It's a 300 megawatt capacity small nuclear power plant. It's a very low rise structure. 2/3 of the nuclear island, which is in this zone, is actually below ground level. The reactor is below ground. Out here, you've got the forced convection cooling system. You've got water storage here, and here you've got your switchyard. The footprint of this is 150 meters by about 287 meters. It's not a big site. These plants are designed such that if you get a loss of coolant accident, like happened at Fukushima, for example, all radiation discharges would remain within this structure and would not go beyond the fence boundary. And that's the basis on which they're being licensed. So they could be built close by larger populations. This is the site, this is what one would look like on a seashore or beside a lake. It's a low-rise structure. Here you've got some transmission towers that are higher than it, overlooking it. That gives you an idea of what it would look like. These are boiling water reactors. They are the simplest way to make nuclear steam. And what happens here is coolant water comes into the reactor. It's heated in the reactor. It's driven up here into a steam separator unit. The steam goes through into the turbine and comes right back around. So it's a single circuit on the primary circuit. You have a secondary coolant circuit bringing condensing water in to cool that water off. It's a direct cycle design. There is, unlike a pressurized water reactor, there are no pressurizers or steam generators in this thing. It uses traditional balance of plant. These are off-the-shelf turbines that are sitting out there in industry right now for a 300 megawatt unit. It uses low enriched uranium, 3 to 5%, U235. The water coolant also acts as the moderator. I won't go into the nuclear physics of that right now, but it serves two purposes, not only cooling and heat generation, but also moderation. And in the case of the reactor we're talking about, this pump is not required. It uses actual natural circulation on the primary circuit. Here is a better view of it. You have this large conventional building, non-nuclear building, which is has the steam generators and the generation facility. You've got some incoming nuclear fuel here. Over here, you have the administration and control building. This is all above ground, as shown by that brown trace. This here in the center is the nuclear island. And sitting in the middle, down here, they're the control rods, and the reactor is sitting about there. This water, we're going to talk about that in the next slide. And up here you have the polar crane, which is used for refueling this particular plant. The plant in the US, General Electric, Hitachi are designing this to go into the US market at $2,500 per kilowatt. We look closely at Australianising that at about $4,500 per kilowatt, giving us a figure of about 1.37 billion per unit. We didn't use that number in our analysis. We used a higher number for the first few of them of $6,760 a kilowatt, or about $2 billion per unit. These are a design to cost approach. They're really working very heavily to cut the cost down and taking advantage of the lower nuclear fuel load in these. They're ideal for not only electrical generation, but also industrial applications such as hydrogen production. And as I said earlier, the first will be operational by 2028. I'll go now to the safety issues. We have here what we call a reactor that is able to keep cool, get rid of that energy, the power coming out of the nuclear fuel after close down by passive means. And so there is a large pond of water sitting above the reactor to take that decay heat out of the reactor. Should one of the main lines going off to the turbines break, so you've got a loss of coolant accident, that you lose your primary coolant circuit, then a secondary circuits come into place, and you have basically a thermosiphoning action coming out of the reactor, back through a condenser here, back down into the reactor itself. And so there are 3 of these going through into condensers into this pool. Only one of these needs to operate to cool this plant down for about 7 days. That amount of water will need to be replaced after 7 days as it boils off. But of course, you're getting almost an exponential drop, or it is an exponential drop in the decay heat that is coming out of this plant. So after 7 days, you're in a very safe situation. These valves are all passively operated. The reactor shuts down passively when you get a loss of coolant. It doesn't require human intervention to save these particular machines. Back to the nuclear island. Here is the reactor pressure vessel. It's 29 meters high, about 4.5 meters in diameter, and it's going to weigh in at about 460 tons. Here you've got the polar crane that is used. In this case, they've taken the reactor pressure head off and stored it there so they can refuel the reactor. These structures here are shields that are used to extract the fuel out of the reactor and place it into the used fuel storage pond in this location. 90% of the components of this plant are based on designs that are already in operation. There's nothing about the BWX 300 which is using unproven or radical technology. It's not a very sexy reactor from that point of view. It's just a machine that will do the job reliably using existing concepts. PricewaterhouseCoopers in Canada, where the first one is being built, Ontario Power Generation are going to build the first one at their Darlington site. So PricewaterhouseCoopers have worked with GE, and they've got a capital cost for the very first of a kind of 2 billion Canadian, which is about 2.1, 2.2 Australian. It'll be built, the first will take 7 years to build, and it'll employ about 1,700 jobs per year over that 7 years. For its 60 years of operation, it'll employ 200 people effectively. Subsequent reactors will take 3 to 4 years to build. That'll be about 2,000 jobs per year for each plant. And likewise, they will also employ about 200 people per unit. Where would we build them and how long would it take? Now, I'll just stop there briefly and take any questions that you may have before I pass on to site selection.
Again, Roger, if you can look to see if there's anyone who wants to ask a question.
I had one previously, Scott, didn't you?
I had a question from before.
Yes, John.
You mentioned that the solar and wind, given priority, are what is causing the coal-fired power stations to be uneconomical, and nuclear power requires a fairly constant output. So you
Yes.
can't allow solar and wind to have the priority. Why wouldn't the present government then just maintain anyone who wants to sell power to the grid have to supply power for 24/7 on an ongoing basis? And in that way, then we would get a competitive 24/7 power supply, and the solar and wind would have to pay for whatever instead of just taking the money and running for the 60 or 70% of the time they don't supply. get a reliable basis.
James, I totally understand your question. I've asked exactly the same thing myself. We have on the NEM a 5-minute market. Anyone can turn up with this power and it's sold in 5-minute intervals. So if you've got something, the capacity, what you're effectively saying, and I totally understand the point, you're effectively saying that anyone who wants to turn up with a generating system better have the capacity to be able to turn it into a 24/7. And if they haven't got that, they better go out and contract to make darn well sure they can do it on a 24/7 basis. The NEM's not designed like that. It's giving this opportunistic position on the market to enable these plants to come in. But further, it's even worse than that, James. The increased levels of ancillary services are not a cost that's borne in the wholesale market. They're external. They exist under a separate market. So that, if you like, is a separate market, which is a subsidy to the main market to enable wind and solar to operate. You've got a renewable energy target, LRET, which is paying of the order of $40 a megawatt hour right now, which is an out of market subsidy to enable wind and solar to come into the market at zero prices, sometimes negative prices, because they've already got a $30 or $40 a megawatt kick. The market is not a true market. It's not even remotely serious as a market. Not while you have subsidies and props all the way through it. So your remedy, which you're suggesting, is if you're going to come into this market, you better be 24/7. Yeah, it's a remedy, or you have a capacity markets, which are other mechanisms. And these are the sorts of questions that daunt us in terms of how we ever adjust to changing this.
Yeah.
Okay, I'll move on then to site selection. I'll just minimize this for a minute. Okay. There are 6 main areas I'm looking at here in terms of site selection, in terms of priorities. I've said already, grid. We've got to maximize the use of our existing grid. Use what we have, and that's what these plants do. Cooling. Okay. They're ideally placed on seashores or on very large lakes, so you can have once-through cooling. That's probably your lowest cost. But putting them on the nodes, we can also use the cooling resources where our existing coal plants are. Now, some people are concerned about the water demand of nuclear plants, and there is a similar order per megawatt hour to a coal plant. But there are now, with these newer plants, hybrid cooling systems, which are using a combination of air flowing through a radiator system with misting through it. So that's a hybrid system, and that drops the water demand by about 70%. And some of them can even go to dry cooling, though you're giving away about 3 or 4% of energy if you go down the dry cooling route, and there's additional cost. So we have, with these smaller plants, by virtue of their small size, a number of options for cooling. Foundations, well, they've got to be built on rock, and you've got to be decently above sea level. Australia has got stacks of good, stable material, and there's no seismic risk in Australia. Transport, I would think the first plants in Australia would be built where we've got close proximity to ports. So, for example, Wollongong, bringing them in on a port, because we'll have to get mechanisms going to transport the heavy loads to further distances. And so you've got to get the crane gear into place, the transport systems into place. Similar loads to these came in through Coffs Harbour, of all places. And so it has been done before in Australia, also down in Victoria. Population. Well, of course, the Illawarra is a perfect spot by virtue of having workforce talent, got engineering and a lot of tradespeople who could be trained up to work in these plants. They provide tremendous community stability for long-term jobs. Each plant will enable 4 or 5 families in generational family groups to move through the industry. And so it would be a tremendous fillip to community stability. You've got to be fairly far away from NIMBYs. I have a lot of them up here in the Southern Highlands. I don't think you've got quite as big a problem down there. Local risks. You don't want to be near airports or fuel terminals, obviously, and you don't want to be downstream of upstream dams or lakes. So they're the main issues that we cover. The 80 plants we're talking about on a split of demand, we're probably looking at New South Wales, about 30, 18 in Victoria, 28 in Queensland, 4 in South Australia, 80 on the NEM, and another 6 over in Western Australia. We've identified throughout the states about double the potential places where you could build these. Places, I must say, you'd be building multiple. So in some locations, you'd have 4 or 5 plants at any one site. If we look at New South Wales, for example, you could be building up around Coffs Harbour or Grafton, coming down to the mid-north coast. You've got places like Munmora, where you could be putting them in there. Or you could go out to Lake Liddell, in this region, Liddell Power Station. You could go out around the Lithgow area to Mount Piper, Wallerawang. The green are what I would call the probables, and the amber are those which are less possible, less likely. Given the small footprint of these plants, but close proximity to a heavy grid and load, you'd want to look closely at putting them along in the Pean River region in Western Sydney. So that's a possibility. We can come down into the Illawarra, and I've got a couple here, which we'll look at in the next slide. And out here near Maroola, out in the Southern Tablelands, near where I live. We wouldn't want to leave Canberra out. They deserve at least one. And we could have some down at Yass with a very good grid connection, or down near Albury in this region. We look at the Illawarra. Lake Illawarra is probably the most suited location there where the existing turbines are, in terms of a grid connection. Bass Point is another possible, though it doesn't have a grid connection at this stage, so you'd have an additional cost there, but it's a very good site in terms of rock and proximity to sea cooling. Or we could go over here to Fitzroy Falls because of a good grid connection through to the main New South Wales grid. Victoria, clearly the La Trobe, because of the massive ability to be able to drive about 8 gigawatts of power into the Melbourne load. Or you could go to Port Stanvic, just here, or Geelong, or over to Portland, where the aluminium smelters are. And less likely ones are at inland locations along the grid, where you've got inland reservoirs. In Queensland, these small nuclear power plants suit their grid admirably because it's a delicate grid. Their maximum voltage, I think from memory, is about 275,000. So up at Townsville, the group around Rockhampton would be ideal, at Gladstone, out here at Stanwell, down here at Callide, or you could go down closer to the load in Brisbane. You've got Tarong, and then sites closer in to the major load areas. South Australia is problematic. It's a very dry place. You could go to where they've got an old coal power plant out here with limited water resources, or you go to Port Augusta, Port Pirie, or down here each side of Adelaide on the coast. They could take about 3 to 5 to stabilise their grid. Western Australia is like South Australia, is similarly afflicted by being a dry state. So you do have these coal plants here at Collie, or Blue Waters is another one. So you'd retrofit there, or you place them along the coastline, each side of Perth, down as far as Bunbury, or coming right up towards Yanchep. So they're the sites for about 5 or 7 in Western Australia, depending on what capacity factor you want. How long would it take to build them? This image here, I'll come to in a second. What we know that in France, they built 63 gigawatts in 22 years. That was an average of 2.86 gigawatts per year. They did that with plants that use roughly double the amount of materials per megawatt these plants would use. And they did it over 22 years for 63 gigawatts. We're talking about plants that are using half the materials for only 24 gigawatts. And I'm suggesting we ought to be able to do that in 21 years. Now, we'll go to this image. What does it mean? The vertical axis is the added actual generation in terms of kilowatt hours per year per person that actually made its way into the grid as a result of building nuclear power plants. So Sweden, they averaged 650 kilowatt hours per person per year in their program. France was up around 480. Finland was at about 350. If we did an Australian program over 21 years, we'd be about 400. Smaller nations tend to do better than the larger nations, which is why the larger nations are down here, because they've got a greater diversity of power system supply. Comparing that with renewables, despite all the crowing, here we're showing about 100. It's actually up around 130 for Australia for wind and solar. So nuclear would be built at roughly 3 times the rate of actual energy coming out of the power socket of wind and solar. The dotted line here represents the amount of the rate at which we should be building this stuff to meet our obligations for 2°C warming rate. I'll conclude now with these 4 final points I'll leave you. Variable wind and solar does not have a track record of achieving deep carbon emissions reductions or providing low-cost energy on a system-wide basis. Variable renewable energy drives up the costs of the most expensive part of our energy distribution and transmission systems, plus system services and storage. These costs significantly exceed the low-cost benefits of wind and solar. At high levels of emission reductions, nuclear energy with VRE run into problems because of a clash of the operating conditions of the 2 types of system. Finally, a system where nuclear energy provides the dominant source of generation is the least cost option, providing energy at around half the cost of a 100% renewable system. I'll turn now to questions and answers. And in brief, after this talk today, you might like to look at, you can Google Nuclear for Climate Australia. I've got an email, info@nuclearforclimate.com.au, or my colleague, Dr. Robert Barr, down there at Kiama, is at rbarr@epc.com.au, and that's his website. So thank you for that, and I'll take any questions.
Right, so you may go back to unsharing your screen, Robert, and then you can see everyone and that.
I've done that.
Further questions? Roger, and then Glenn. Roger, you're muted.
Sorry, it's an interesting presentation, I thought, and obviously covered a lot of territory. What about the nuclear fuel, though? Would that still have to be imported, or is there anything in the
If we look at the
pipeline?
history, no, it's a good question. If we look at the history of countries, when you get embedded with a large amount of generation like 24 gigawatts, I would think it would be highly likely that Australia would do probably what the Koreans do. The Koreans at present have their fuel enrichment handled by others. There's a lot of enrichment capacity around the globe in France, in Europe, and in the United States. And what the Koreans do is they import the enriched uranium, and then they fabricate that into fuel. So you can bring your enriched uranium hexafluoride into the country, turn it into uranium oxide locally, make your own fuel, and then go on. It's really a sense of economics. Would you want to build your own enrichment facility if everyone's got the enrichment out there? But that may get taken up very quickly, as I suspect the world is going to be building a lot more nuclear. So it's really a cost of what's the capacity out there to do it. But the Koreans, I've visited their nuclear fabrication plant where they build their own. I've visited the ones in the US. The French are fully integrated right from uranium ore all the way, and I've been inside their enrichment facilities. So it's really a question of economics, but at 24 gigawatts, I would think the economics of doing it in Australia would be compelling over the long term.
Glenn.
Robert, your very last graph shows that the climate predictions, the 2-degree line is very much higher than your predictions.
I'm sorry, I might just go back to the slides. So
Yes, that's the one.
Agree. And this is where I would like to see us be building them in terms of getting on with it. So back, Glenn, to your question.
Yes, I guess it does. It's interesting that all the other countries on the right-hand side graph are way below.
They're not, yes, they're not achieving the 2-degree with their renewables. And this here is the renewable side. This here is the nuclear power side. And so the renewable rollouts occurring around the world are not keeping pace with the need to decarbonise.
Sorry, I meant the left-hand diagram.
Yes.
Yeah.
And here,
USA, Germany, Japan, Spain, these are major producers of energy, and they're not going to meet that 2-degree.
oh no, what this graph, to be quite clear, is telling us is that the rate of whether you build wind, solar or nuclear has to be up around 300 kilowatt hours per capita per person per economy, regardless of what you build. And at present, no one is building enough of anything to meet those targets. What they are building, of course, is fossil fuel.
Okay, thank you.
Okay, I think Noel, you had a question. Noel, you're muted, mate. So can you just unmute yourself?
Robert, I don't think you mentioned much about waste product and how that's disposed of. I know it all happens, but it's the question in the back of many people's minds.
Okay, I'll just go back. Can you see that slide called used nuclear fuel?
Yep.
I'll leave the diagram in this condition for the time being. Oh no, wait, I'm not, wait. Okay. To go through a few parameters, a typical 300 megawatt plant would build about 8.1, it'd yield about 8.1 tonnes of fuel per year. That's at about 45 gigawatts per day. We have a measure called gigawatts per day per ton of fuel. So we'd have about 8.1 per year coming out of a 300 megawatt plant. Volumetrically, with all other bits thrown in, this represents about 4 cubic meters per year. And of this, about 3.2 is high level waste. If we use 2 passes as the French do, the high level waste volume reduces to about 0.8 of a cubic meter per plant per year. And if you put that through what we call fast spectrum reactors, you'd end up with about 1 or 2% of that as long-lived waste, and the rest of it would be fission products, which would last for about 500 years. Now, I'll come to your issue of how you dispose of this in a minute. This gives you an idea of the tonnes. If you did that 76% of Australia's energy was to come from nuclear, it'd generate about 367 tonnes of high level waste per year as first pass. If you recycle it, it'd be about 92 tonnes or about 56 cubic meters per year. Now, that's not a big volume. So you can recycle it as the French and the Russians are now doing, and you can get between 56 and about 48 cubic meters a year, depending on your process. That's for all of Australia. But
That's presuming we built fast reactors.
no, that's not assuming that. That's assuming you're using these thermal spectrum reactors. It'd be between 56 and 48 cubic meters. Now, the next thing you can do with that is you can take the plutonium and the radionuclides, such as americium, neptunium, and those higher level ones, and you could build those, put that material into fast reactors, and you only then end up with about 1 or 2% of these amounts left. You end up with very small amounts. You effectively burn the stuff that people are concerned about that lasts for 100,000 years or so. You still end up with fission products, and they are the most the most intense radiation is actually coming out of those because they've got very short half-lives. And so that material would need to be put underground for up to 500 years, after which time it's decayed to nothing. So you end up with a material that there's not a lot of it, but it would have to go underground for up to 500 years. Plus you would end up with some wastes in the reprocessing zone. These would be liquid wastes, which would then be formed into glass, which would be over and above that. And they would also have to go underground. So with fast reactors, you end up with almost no long-term waste, but you do end up with the industrial products and fission products that will last for about 500 years. So to my mind, and I may be prejudiced here, but I consider that's quite a manageable time frame. But it presupposes, as the French are looking at doing, that around about 2040, 2050, you start to get into fast reactors. The Russians are into them right now. They've got the BN 800. They've had them for quite some time. So it comes down to a national agenda of whether you choose, as the Finns and the Swedes are doing, to go underground with all of their waste. They're going to consign the whole lot, but they're going to leave them with the potential to reclaim it from underground. So they're not actually going to seal it off, they're just going to put it down there. Or you decide, as many nations did, Japan was the same, the British were the same, they were looking at really a long-term recycling plan for this material. So you have those two routes you can follow. I would think the other side benefit of fast reactors is you also end up with virtually an infinite supply of nuclear energy and nuclear fuel on the globe. I mean, you would just never run out of it. It would go on for tens of thousands of years. I hope I've answered your question, if you're happy with that.
Well, I've got my doubt, Robert, that where you've mentioned all that is what would happen. The problem is to sell it to people generally, that that's what will happen, and you can be safe with nuclear waste produced, say, in a plant located in Wollongong. And I think most people at the moment would say, no, you won't do it near here.
Yeah, yeah. And I don't think you're wrong. You know, you go through different nations. For example, the Finns and the Swedes, their populations have come to terms with using deep geological repositories. The South Australian Royal Commission came up with the response that deep geological repositories were the way to go, and they've done that. When I'm talking about deep geological repositories, we're talking about going down 500 metres into granite in basically mining drifts, going 500 metres down into granite. Some of the ones they're looking at now with these fairly small volumes, they're looking at deep boreholes going down a couple of kilometres and putting it into deep boreholes down at those depths. It's never going to come back from there. And so they would be quite sensible solutions. If you've seen where the Finns have decided to put it at Ocklo, you know, they're going 500 metres below the coastal locations and putting it underground there. I've been into a facility in South Korea in what I would call fractured basalt, and they're putting it down below sea level in the facility I visited there. So a lot of these nations are at ease with placing it at considerable depths in granite.
I'm cognizant of time, so is there one more question? Otherwise, I'll ask Scott Chalmers to thank Robert as well.
Scott's got a question.
I've got a
Okay.
question which I'd asked before I just say thank you. Robert, we've seen that the Chinese and the Russians are the only people that today have a small modular plant operating, and they've taken probably 8 or 9 years to build these plants. The large plants like Hinkley in the UK are taking even longer, but our coal-fired power stations are going to shut down earlier. So we need to get moving really quickly if we want to think about small modular plants. GE, Hitachi are still in proposal. I believe NuScale has been approved and started construction in the States. So where do we go from here?
Okay, good question. NuScale actually don't have a plant. They don't have an agreement yet to build one. Theirs is a somewhat complex plant. In the West, the fastest nuclear power plants that are going to be built, probably the first one will be the BWX at Darlington in Canada. That's the plant we've looked at today. In Wyoming, they've agreed in Wyoming to build the Natrium reactor marketed by TerraPower. And that's a firm partially owned by Bill Gates. And that's an exciting plant that's going to be built at the side of an old coal plant. And so they're hoping to have that up and running by about 2026. When we come back to the performance of large plants around the world, we saw the construction of 5.6 gigawatts of APR 1400s built by the Koreans at Baraka in the United Arab Emirates. Now they've got 2 of those, I think it's 3 now, they've got at criticality, and the 4th is about to come on stream. And they've built those over a period of about 10 years. We tend to focus too much on countries that are not doing it well, but we forget, for example, that there are 2 plants being built at pace on the Ganges in Pakistan right now. We've got plants being built throughout India right now. We've got them being built. We've got, I think it's 4 plants in Egypt. We've got plants going ahead in Turkey. The largest exporter, there's something like 50 plants underway in the world right now. And yet people focus upon the poor project management skills, for example, of the Westinghouse plants at Vogel in the United States. Hinkley's not doing a bad job. There's a lot of people prepared to go out there and lambast these plants, but Hinkley's not doing a bad job of getting in at straps, and they're probably going to build another 2 now at Sizewell. We are too late with these nuclear plants coming to the fore. That's why I'm saying that we ought to get out there and get amongst it and be planning for them and not waiting to see necessarily what the rest of the world can do. I can't see for the life of me why we couldn't be knocking these plants out and have them all in place, as I say, over a 21-year period from around about 2028 and get into it.
Okay, well, I'll say thank you very much, Robert, for it's a very interesting subject for a lot of us. You've answered a lot of questions, and I'm sure you've got a pretty good mix on it. And all we can say is thank you very much for going through it in a simple but clear and logical fashion, which gives us a picture of where we stand. And I think for my part, well, all of us, we need to do our own part and maybe talk to people and politicians and keep the pressure on them to change the present legislation so that we can start at least planning and start training people, because not only that, we'll have to set up a training system for people to have the knowledge. And I'm sure you, who did your master's in nuclear engineering after quite a few years of general engineering, can appreciate how much work we have to put into training people to be able to operate these 40, 50, 80 plants that we might need. So thank you very much. I'm sure you're working with everybody, and I would hope all of our members can also provide support to you in this endeavor. And once again, many thanks.
And thank you for that, James. I would just ask in that support to please, I really need the ideas and help out of your membership. You know the Illawarra, you know industry, and I'd like the hard questions. I appreciate Noel's question, particularly on the disposal of used nuclear fuel. So I'd appreciate your thoughts. You can send me an email at rob.parker@nuclearflightforclimate.com.au. I send out a blog. I would like to be able, through WIN perhaps, to receive the emails from as many of you so that I can continue to send you out updates from the website, which I've just overhauled. There's a lot of new stuff sitting on there. I'd love to be able to send that out, but I would really like feedback, particularly from people learned in industry in the Illawarra, so that we can develop these ideas. Thank you.
Thank you, Robert. And can you just unshare the site again?